And so, before I start, I'm a Java developer. I'm on Avenue Code since 1222. There is 2 years that I'm here. I'm a developer who loves tests and refactoring, and one of my college clients are here, so he can reply that saying that I love tests and refactoring. I'm working as a developer since 2011. I'm graduating on database technologies, post-graduating on web and mobile systems, and currently I'm studying for a master degrees on computer science and technology, and mutation tests will be the top of my dissertation. So this is the why we're talking about mutation testing. So uh, this is the summary of this presentation. I'll be a brief introduction of this topic, how the mutation test works, and how to implement some implementation and tools we can use and you can usually use and understand how it works. Some challenge and advantage of using mutation tests, and then the conclusion of all the aspects of this subject. So what is mutation testing? So basically, it's a technique to evaluate the test suite quality. So the basic idea is testing the tests you already has in your code to check if you are safer, if it's enough coverage, and is strong enough to detect small changes and small bugs that could be appear on during the development of new features and improvements. The base concept of the mutation testing, it simulates small changes, bugs or faults in the source code and run the tests against these codes a little changed. And the main goal is to check if the tests are capable to catch these little changes. So why mutation testing? So print here, we have your original code. I will talk a lot of Java, okay? So we have our original codes, our source code that could be small or big enough to a whole project. We will pass this code through an algorithm that is basically the mutation testing library we want to use. And the output will be a changed code. This changed code will be, for example, change an addition for a subtraction or multiplication for a division. Just sometimes just a character inside a word class will be changed, and this changed code is the mutant code. Be- uh, we saw this, we say that's mutation because it's just a little change on the word aspect of the class of the file, the code file. And as we saw, this is we will see this algorithm to generate the changed code is the mutator that we call. And all the mutation code you saw during this presentation will have this little Wolverine in the background, just you to pay attention on what is a mutant or not. Okay. So testing the tests. I will take a little explanation about how tests usually works on the most of the program language, libraries, and frameworks. So we'll have our source code. This source code will run against some test suite, usually a huge test suite, and we can have three possible outputs. The test can pass, meaning that the expected value of the test corresponds to the actual value outputted from the source code. The test can fail, meaning that the expected value didn't match with the actual value of the code, the actual output, and we can have an error. The error is basically when there is something completely unexpected on the behavior of our source code, that generation exception or a error that with no a device stops the running of our code or generates an exception on our code. But there is a trick on these three possible outputs. For example, this trick is when our test pass, it could be a false positive. And why? Because usually most of the deliveries and testing frameworks has a concept that it will run the source code, compare the results, and if the results match, uh, anything happens. So basically, the method, the coding test, will just stop in the first line, end on the last line, and the test is passing just because the test run all the lines and anything strange happening. So if some assertion didn't match, it will throw, for example, an assertion exception. If some error occurs during the source code, we will throw a runtime exception or some time of exception or error that uh, will finish the test before the last line. So this is the way the test libraries found to discover if a test is passing or not. But the trick is, if you didn't check something or your expectation is wrongly planned to the test, so your test is passing just because some coincidence or just because the test suite is not strong enough to detect the changes that you want to test. So the next step on that, how mutation testing works and works on that scenario you are seeing before. So mutators, that is algorithm that generates the changed code. This term comes from mutation operators, and is basically a program that introduces modifications into the target code base. For example, that one I said before, you change a multiplication for a division, for example. So how it will work in this scenario? Instead, you will run your test, okay? This first step continues as usually, but you will run a mutator that will generate a mutant code. It's basically the same class with some difference. After that, you run this mutation code through all your tests against all your tests, and you can have the three possible outcomes again. But here there's a difference. If your test continue to pass even against a mutant code, it means that mutant survived. So a small change in your code was not detected by our tests, and the test continued to pass. So the mutant survived. And if you get an error or get a failure, you killed the mutant. So the test killed the mutant, and you can maybe you're checking this and say, okay, why mutant survived is red and killed mutant is green, and this is strange because killed someone is not good. But this is the point: if your mutant survived, it means your test is weak. You need, for example, you need to improve something because small changes in your code base wasn't detected by the tests. And if your tests are killing the mutant, it means your test is strong. Yes, unfortunately, if X-Men were here, we are against him. So basically, I have a lot of sentinels here to kill all the shy guys. So basically, this is the main idea. Check if your tests are strong enough to detect small changes or are so weak that they are not detecting any small changes. And remember, I'm talking about a lot of small changes. Think about when you're working on an improvement that's adding a new method, adding new behaviors to a class or some file. That is complicated because there is I don't know, 300 lines in that file. And you didn't note, but you changed something. You pressed the backspace and didn't notice something, and no one noted this change in the middle of a lot of other lines during the code review. And this is the point. If your tests are not strong enough to detect this, you need to review the test and check how to improve that. So a good test kill all the mutants, basically. In this moment, I think you shoot that poker face, and not before, but okay, you send the correct emoji in the correct time. So implementation and tools. Thank you guys. Thank you very much. So the implementation tools. There's a huge number of operators. Remember, operator is the mutant operator, the mutator. And when I say a huge number, yes, we have more than 1,000, I think, operators. I'm reading a lot regarding this theme. So, and each of it will change something very small in the code. In this presentation, I will talk about four of them. And the fourth one is a secret. So because of that, I'm not showing that here. But for example, we'll talk about the arithmetic operator replacement, the relational operator replacement, and the logical operator replacement. More detailed. But if you take a look very quickly, it's capable of to understand more or less which what each of these guys will do. For example, I take the one of the lesson empty argument. For example, this is our operator that basically call a method. For example, you have a method with some parameters. You just remove the parameters and call the method passing null for all the values, and just check what you have. What is the outcome of that during your tests? So let's start with these operators that I selected. For example, and before that, just to you have some you have multiple options of these mutation testing libraries and frameworks in every language. In Java, for example, we have the p-test, that is the most famous one and most used. We have measure, the starters, that is our good one, and you have mujava. Mujava one is very is one of the more increasing the last years, because mujava is supported by one university from Spain, and this university, I think together with some Chinese university, has a lot of researches theoretically in the aspects of mutation tests. So the theoretically based stuff on in this library is very huge. Python, you have mutmut and Cosmic Ray, and JavaScript, you have the p-test version for JavaScript, and you have the most aggressive and I don't know, the best name ever for the library, Striker. In the moment I found this, I meant, man, we need this on Java because the name is very good. P-test, sorry, no. Okay, let's Sentinel. Yeah, Sentinel is a good name. There is some copyrights, I think, but we can just eliminate the copyrights, right? We are eliminating a lot of things here. So the arithmetic operator's replacement, for example, is basically a mutation that change addition by subtraction and multiplication by division. Based here, we have the mutator will change the arithmetic operation by its counterpart. For example, here I have an arithmetic example class that has a add method that receives two integers, a and b, and basically return e plus b. Just simple. And we have a test here, a simple test that basically we basically have passing two values, 5 and 3, and we expected that the result will be equal to 8. What is the output of a mutation, of a mutator, the arithmetic mutator on this code? We will change the plus for the addition for subtraction. What is expected on that? If you run the same test against the new implementation, the mutant implementation, the test will fail, because in this case, 5 minus 3 will be 2. This is the idea. It's simple. Could someone say, okay, this is okay? I don't know. There are some people that say that, seriously, we need that. But the idea, I will show the why you need this type of thing in the next slide. But this is the type of operation we have. The logical operator, for example, the counterparts, again, they replace ands, ors, and the nots, and the negation for each counterparts. For example, we have this operation that receives 3 integers, and you have a complex code. Guys, just one point, I generate all of these examples with ChatGPT, so some examples doesn't make sense on the real world. It's just to show to you very in the simplest way how the operation will work. So in this scenario, if A is greater than 0 and B is less than 10, or C is equal to 5, basically, this will return true. So this is some examples of tests you can have here. Passing, for example, 5, 3, and 0, 5, 3, and 5. This is expected to be true. But if you pass minus 5, the result will be false. It's expected to be false. And if you pass minus 5, but pass 5 in as the last parameter, it's expected to be true. And the mutation of this will be simply change replace the operators, the ends for ors, the ors for ends, and negating the equal operator. Remember again, we need our expectation is to make the test fail. So change the file as the test will fail and check if it's okay. So I can check this question in the end here. I remember this question because it's a good one. The relational boundary operator is one of the most used, and it is most used because of this example. In this case, you have a simple code that checks if a value is in the range, which means is between a minimum and a maximum value, and you have a lot of tests to check that. But what is the mutation of this simple code? For example, is basically in case of the greater than and less than, the counterpart is greater than equal and less than equal. So in this scenario, basically it removes the equal from the statement. And depending of the value that you have here, your test could continue passing. And or maybe if your test is good enough, you fail the new test because the mutant code is not considering the real scenario that you put on the original code. Okay, and this is the void method call operator. This is the operator that make me knows to the mutation code. So what did this guy do? You have a code because this one, for example, full, and you have some void method that does something. And why void method? Because void method doesn't have a return. And if it doesn't have a return, if you just, for example, stop to call this method, your main method will continue to run from beginning to end, but something in the middle will stop to happen. And this type of operator usually doesn't affect any test, because this is the point. It's very common to us to, if you have some void method in the middle of our code, we forgot to test that. You test the result of the method, you test the result of some operations. But here we have a good example. For example, you have instead of do something, you have a method log tracking data, and you just stop to call this method. Are you testing, for example, checking if the logging continues to be tested, or you are just checking the results of the method? And in this example, I discovered mutation tests because of this operator, because I had a problem with this scenario. I did something on my code that stopped to call an, a void method that adds in logs to my system, and everything continues to work well, to run fine with no errors. But some weeks after the PR got merged, we discovered that some logging stopped to appear in your dashboards. In that moment, we revisited the codes and found my code that was removing this line. And not removing the line, I changed an if statement that affected this line, basically. And the results, there is a lot of ways to solve the results, but basically on p-test, that is the most one on Java, we have this, for example. We have a coverage line just to check if all the lines are coverage, and you have the mutation coverage. In this scenario, for example, we have two mutants that for some reason, oh, I forgot to put the lines. We have two mutants that for some reason survived our test suite. For example, in this code, just checking some data, you have a list statement, and we can check that on line 14, for some reason, someone survived here, and someone survived on line 21 too. In this check, this number here are showing the number of mutants that we have just in this line. So on line 14, we have 10 mutants. And from these 10 mutants, one mutant survived, that is the change conditional boundary. Probably the change this passport ID less than 0 to less equal. And any tests are checking for that. to share that, to send the information of this the correct overcome for here. So basically, this is this type of result and the advantages and challenges of mutation tests. Advantage, detecting weakness in the test suite, so it's helpful to check if small changes will affect your code. It's good as good to show, for example, there is no tests working on some methods or some class, like coverage, but with more experimentation. Improves code quality because you need to recheck against some parts of your code. Enhance the test suite quality because helps you to explore and improve your quality, and identifies unreachable code because this is the point, helps you to note that some code was not tested in any scenario of your test suite, and foster confidence in code changes because with this type of technique we can have more confidence in your change codes because you have the security to know that it will any change you do will work well because you have confidence in your test suite. And the challenge, just to be very fast here, cost and time spent. For example, one line of the last code generates 10 mutants. So depending of the size of the code, the type of operations, we have a lot of mutants that will expend a lot of money and computational time. The equivalent mutant problem, this is the hardest problem on mutation tests because sometimes you have a mutation that is quite equal the original code. So how do you know what is the correct and choose the best mutator set? So you can use some mutations and other some mutators and the others not, and sometimes you need to choose that. And my conclusion here, a test data set that detects simple faults will detect complex faults. The combination of several simple faults. I saw this type of phrase in a lot of articles that saying if you have a good enough test suite of JUnit tests catching the small details of your code, probably it will help you to avoid complex situations on your code. So this is it. Thank you guys. I will take a look on the question also if you have time for it.
Yeah, we have it. Thanks for the great presentation, Carlos. We have a few questions on our chat. Gabriel asked a few of them, so I'm gonna read them to you. So he asked if these mutations are usually applied to the production code or only to the test code or both, and when should we apply them? In which part of the development or the CI process should these mutations be applied?
Okay, this is a complex question, I must say. Usually, these mutations will be applied to the production code. What I mean for that is to mutate the source code of your application. We will not mutate the test code. So the tests will continue to be the same, but we'll add or replace some details on your source code and check if your tests continue to pass or not with these mutations. But the test will continue the same, basically. Regarding the CI cycle, there I read some articles and some research regarding how to apply the mutation tests on large repositories, and the best practice that some industries had applied is to for example, in the first moment, in the moment of starting to apply the mutation test, it runs the mutation test for on all the code by model, by directory, by, for example, they use some random way to choose what code will be run the mutation or not. And after all the code or all the critical code gets coverage by the mutation test, they, for example, create a new CI that run after the JUnit, for example, the JUnit test, and it's incrementally. So it will run mutants just over the new code because they have the confidence that the codes are already merged, it's safe. So just new code will have the mutants because of the problem of cost and time spent to run the mutants. I think is that.
Great. Yeah, we have another one. Also asked if there is any Java library that has a good integration with SonarCube, and if so, if it is easy to integrate.
To be honest, I think PA test it's very easy to integrate, but we have some lack of information on that part, because integration tests are very useful to a lot of people, but you have a problem that because of the cost, a lot of companies didn't try to introduce it. They prefer, for example, to introduce some sonar configuration to check the coverage of the code. So, for example, if you have 90%, 99% of coverage, it's enough. For example, it's an option. But I saw some tutorials to integrate mutation tests with Sonar, for example. But I didn't see this in a real life and production on some company. But I'm trying to do something of this test, but I know it's possible. I just don't know if it's common to use, but I think something that is growing up on the last years.
All right, sounds amazing. And if there is no other question that people want to ask, oh, go ahead. Go ahead, John.
Hi, I actually have a question. First of all, very good presentation, Carlos. It's very nice to watch you talking about tests. But there is one question that I had, which is with this revolution of AI, which is happening now. I guess mutation test is an area that could profit from some AI implementations as well. Do you know if there's any type of attempt of creating this already? Or how would you imagine that AI could be applied to scenarios like these? I believe the ones that we have nowadays, some of them look pretty simple, but maybe with the AI capabilities, we could cover even more complex situations and scenarios, right?
Yes, I think based on my tests with AI, I try to run mutation tests with some tests together with AI, some generative tests AIs. And as far as I got and I read about, some companies are using a lot of the new AI platforms to generate test suites, and they are using, for example, the mutation testing to check if the test suite generated by the AI is running well or is confident enough. For example, if it's matched with the expectations. So using mutation test is a tool to check if the test generated by AI is good or not, for example. But I think one area that will improve on the next years, to be honest, on the next months probably, we use the AI to generate mutators or to mutate the code with no necessary passing through all the mutator logic, because the AI will have the power to understand the complex details of the code even more with the correct prompts, and generate mutations with a less cost and using more computational time.